Hello guys, in this video we will learn about the Fibonacci heaps. In previous lectures we already covered the other priority queues like binomial heap and binary heaps. So the priority queues can be implemented using some of the special type of data structures like binary heaps, binomial heaps and Fibonacci heaps. So let's understand what is the meaning of priority queue. So priority queue is a abstract data type. So as we can see that here it is a type of queue. In the queue data structure, the elements are stored in a first in first out manner. So for each element in a queue, we follow the first in first out mechanism. So if an array is given for a queue data structure, if an array is given, then the elements are inserted from the rear end and it is deleted from the front end. So each element is deleted from this end and inserted from this end. Okay, so in this way every element maintain a queue like in like a real world queue, and it is inserted from the rear part and exit from the front part. Okay, so if any element in between requires some special access, then the queue data structure does not fulfill the requirement of this element. So for this type of application in which some elements require high priority or some elements is required to serve first, then we use the priority queue data structure, and in this priority queue data structure, that element with the high priority served before the element low priority elements. Okay, so for example, in these two pictures, this picture represents that in a medical line the person with the different injuries are shown. So if a kid with an injury will get the highest priority because it is a kid and it has some injury also. So we can define the priorities according to the application or according to the need of the application. So in this one we can define a priority 1 to this kid, priority 2 to this man, priority 3 to this woman, and priority 4 to this man. Okay, so in this one this kid will be served first, then this man will be served, then this woman will be served, and this finally we will serve this one. Okay, so instead of maintaining a queue, we will maintain a priority queue. Similarly, in the web traffic which is not equal always, we can define some priorities. So the priority traffic will get accessed first, then all other traffic will be accessed in the first in first out manner. Okay, so generally we follow this type of mechanism because in the web traffic the bandwidth of the network is limited, so we have to serve the priority traffic first so that the user requirement can be fulfilled as much as can. Okay, now these are different applications for the priority queues, like graph searching. For graph searching applications, some event driven simulations may be there, some statistics like to maintain the largest m value in a sequence, and Dijkstra algorithm, Prim's algorithm is also used these type of priority queue data structures. Okay, so this is about the priority queues. Now as we have studied different type of priority queues previously, like linked list, binary heap, binomial heap, Fibonacci heap. A binomial heap is a type of mergeable heaps which will follow different types of operations like insert an element in a binary heap, delete or extract the minimum element, decrease key, delete an element from the heap, uniting two heaps, or finding the minimum element. Okay, these are some of the important operation followed by the binomial heap, and binomial heap do these operation in order of log n time. So all the operations are done in order of log n time except the make heap and is empty operation. So the log n time is not as much as efficient because the Fibonacci heap will do these type of operations in order of one time except the delete min and delete operation. So all other operation will done in order of one time. So we can see that from this table that Fibonacci heap is efficient than the binomial heap and binary heaps. So for that purpose, in some application where this insertion and decrease key and the union type of operations have larger, then we can use the Fibonacci heaps instead of binomial heaps. Okay. Now the binomial heap, so the binomial heap is especially desirable when the number of extract mean means the number of find extract mean and delete operations is small relative to the number of other operations, because in these two type of operation it will take the same time as the binomial heap. So in those application in which the extract min and delete operation have relatively small, then we can use Fibonacci heap, because it will return the order of one time for all other operations. So the main application for Fibonacci heap is graph algorithms, computing the minimum spanning trees, or finding out the shortest path. So binomial heap is similar to the Fibonacci heap similar to the binomial heaps if these two operations are not applied, because these two operations require a special information, that is a mark node, which is not in your binomial heaps. Okay, so we will see in next slide what is the purpose of mark node in these type of operations. Next is this let's study the structure of a Fibonacci heap. So how the Fibonacci heap is maintained. So first is, it is a set of heap ordered trees. Heap ordered means every element in a tree have follow some of the heap properties. So here the min heap property is maintained. So every element in a tree, or we can say the root list in my Fibonacci heap, have the minimum element. So this is minimum element, so this is also a minimum element. So we can say that my heap is a heap ordered tree. Second is, the pointer is maintained on the minimum element in the root list. So this pointer min of h is having the minimum element in all the root list of the Fibonacci heap. In binomial heap, we have maintained a head pointer on the first element of the heap. Okay, so this head pointer, so to find out the minimum element, we have to scan all the root list, which will take order of log n time. But in case of Fibonacci heap, as we maintain the pointer on a minimum element, it will search the minimum element in order of one time, because we just access the element on the min pointer. Okay, we also have a set of mark nodes. So as we can see here, these three nodes are mark nodes. So these mark nodes are used to keep the heap as a flat and stay tuned. We will see the concept of mark node when we study the decrease key and delete operations. Okay, now let's see the structure of Fibonacci heap in implementation perspective. So a tree within a Fibonacci heap is rooted. So rooted with the mini heap ordered, and the degree is not maintained. So every node, so as degree by degree I mean that in binomial heap the tree are ordered in their degree. So if it is a B0, the next will be greater than B0, either B1 or B2. Similarly, the next tree will be either B3 or B2. So like this is a B2 binomial tree. So in heap, every tree maintain a degree. So we have increasing order of degrees for all the trees. So in Fibonacci heap, this order is not maintained. So we have unordered binomial trees in Fibonacci heap. Each node of Fibonacci heap, each node have this type of pointers. So we have a pointer which is pointing to the parent of the node, key of x, which will represent a information that can be held by this node. The degree of x is the number of child. Mark of x is a boolean field which will tell you that whether this node is marked or not. We can set the values true and false for the same. The child of x is a pointer to any one of its child. So because it is a circular double linked list, for example, in this node 3, the child pointer is pointing to node 52. So we are not required to point 18 and 38. We just point to a one of its child by the child pointer. Now every node have two pointers, left and right, because we implement the circular doubly linked list here. Every node require the left pointer as well as the right pointer. So the right pointer of the last node in the root list will pointing to the first element in the root list. So this whole list is known as root list. So root list is also a circular doubly linked list. Similarly, every child maintain a circular doubly linked list in which the rightmost child will pointing to the leftmost child. So this is your child list. It is also a circular doubly linked list. Okay, so similarly here, if only one child is there, the left and right pointer is pointing to the same node. Similarly here, okay, and the min pointer is pointing to the minimum element in the root list. So this is the implementation structure for each node. So in the struct node, you have to define these types of field in order to implement the Fibonacci heaps. Okay, now there are some notations which is required for the operations in a Fibonacci heap. First is the number of nodes in a Fibonacci heap, which is denoted by n of h. The number of childrens of a node x can be said as a degree of x, or in some book it can be represented as a rank of node x. Similarly, the degree of h is a maximum rank of any node in a heap, maximum rank. So the maximum number of child of any node in a heap is known as a degree of h, or we can also say that it is a rank of heap. Okay, so in next one, T of h is a number of trees in a heap. So you can count the number of roots in a heap, that will return the T of h. Min of h is pointed to the tree containing the minimum key in the heap. M of h is a number of marked node in a heap. So here the M of h is 3, T of h is 5 because we have 5 nodes in the root list. Total number of nodes is 14. The degree of a node x is 3 and degree of heap also 3, because in this this node contain the maximum number of child. Okay, so that's why the degree of the whole heap is 3, or the rank of a whole heap is 3. Now every newly created node is unmarked. In case of marked field, if a node is newly created, it is unmarked. A node will become unmarked whenever it is made the child of another node. So there are two possibilities of a node in unmarked. First is when you create a new node to be inserted here, that node will be unmarked. Or if I suppose this node is marked and I add this node to the so this cannot be added here. So if 23 is added in 7 and it is marked previously, then we can say that we can make this color of the node is unmarked. Okay, a node is marked whenever a child of that node is deleted. So if I delete the 46 from here, then the parent of this node is marked. Okay, so we will see the details about the marked and unmarked node in the decrease key and delete operation. Now the another important thing about the Fibonacci heap is potential function. So potential function is generally used to analyze the performance of a Fibonacci heap, or performance of a Fibonacci heap, or performance of any type of this priority queue. Okay, so generally let me give you the formula. So this is, as you can see, that 5 of h is equal to number of tree of h plus 2 into m of h. So here t of h is what? Number of trees in a heap, and m of h is number of mark nodes in a heap. So for this example, we have t of h as 5 and number of mark nodes is 3. So the potential function is calculated as 11. So for this heap, the potential function is 11. Okay. So for any data structure, initially the potential function is 0, and as the application begins and some node is added to the data structure, the potential function changes. So we have to measure the potential at each step in the application. So the idea is, why we require the potential function to analyze the performance of a Fibonacci heap. Generally what we have done, we have calculate the change in potential at every step. So if I have a data structure at ia minus 1 and it is changed some of its structure at step I, then the difference between the structure will be added to the actual cost in order to calculate the amortized cost. So for example, I have a binary heap like this with some information. Suppose it is a min heap, then the information is like this. Okay. So if I add some element to this binary heap, like I want to add element 1 here, so the 1 cannot be added here. The structure of this whole heap would be changed, and 1 would be replaced by this node, and the structure is like this. Okay. So if I say that this is the data structure at I minus 1 and this is the data structure at I, then there is a change in potential. If this data structure is Fibonacci heap, then it may possible that some mark node may be changes, or the root list may be changes due to some addition or deletion of a node. So we need to find out the change in the potential, and this change will be added to the actual cost which is done at that step, and that will return me the amortized cost, because we generally deal with the amortized analysis of any data structure. So CI cap will give me the amortized cost of the operations. Okay. So similarly, we can find out the amortized cost for the all n operations. So summation of I is 1 to n. The CI cap would be summation of this whole term, that can be denoted as d of n. So this is a phi d of n, the maximum changes that can be possible. So in this case, because this is a Fibonacci heap, you can say that d is a degree, represent the degree of a node in a root list, and the degree of a node cannot be greater than log of n. Okay. So d of n cannot be greater than the log of n, because it is a binomial tree, so it will follow the binomial heap property. Okay. So this d of n never be greater than log of n, and initially the degree is 0 when the heap is empty, and at each step we will add the CI cost. So by this we will so this is the idea behind the potential function. So we have to calculate the potential function based on the number of trees in a heap and number of mark nodes. Okay. So these are the two important changes which can be made after the operation. So if I follow the decrease key and delete operation, the mark node will be changes, and in other operation the T of H will be changes. So these two parameters can give me the intuition that the data structure will be changed somewhere. Okay. And we in potential function we require the change in the potential, and then we add with the actual cost. So in all operation analysis we use this type of analysis in order to measure the performance of Fibonacci heap. Now Fibonacci heap support all mergeable heap operation like make heap, insert operation, minimum, extracting the minimum element, union, and these type of operations can also be followed by the binomial trees. And we can say that for each operation, Fibonacci heap is simply a collection of unordered binomial trees, because we are not following the order of degrees in this type of Fibonacci heaps. Okay, and if a n node Fibonacci heap, what a collection of unordered binomial trees, if n node Fibonacci heap is a collection of unordered binomial trees, then the maximum degree of any node is equal to log n, or we can say that it is in order of log n. Okay, so next is, if first operation, when you want to create a new Fibonacci heap. So in order to create a new Fibonacci heap, this make fib heap procedure is called, which will allocate and return the Fibonacci heap object h. So because the heap is empty, the number of nodes in heap is 0, you set the min of h is equal to null, the number of trees in a heap 0, number of marked nodes are 0, and the potential function is 0. So initially all the potential function is 0, there is no change in the data structure. So the actual cost would be order of 1.